Multivariable calculus, we're on section 15.7, day 1. If we look at the top learning target here, I can evaluate triple integrals over bounded regions. So let's read this. Just as we define double integrals to functions of 2 variables, we can define triple integrals to functions of 3 variables. Of course, a function of 3 variables, you will have as an input, say an x, y, and a z. Something would come out, say, call that a w. We actually won't visually be able to see that output nicely. But all the same, we can still have uses for triple integrals. Let's just say that you're integrating over this rectangular box B where your x is defined within boundaries, say between A and B. Your y is defined between C and D, and your z here you could see is between R and S. You can see this is Fubini's theorem. As you integrate this function on that rectangular box, you will have this triple integral. Of course, Fubini's theorem is also going to allow us to change the order of integration however we'd like. So let's just see what's going to happen in this example 1. As we're looking at this, our x boundaries are between 0 and 1, so we could actually start right there and say, hey, we've got this right in the integrand, we have x, y, z squared, but our first order here is going to be to integrate with respect to x. Then we could go with respect to y, that's -1 to 2. And then finally we could wrap up with z. By the way, we may change this order around if it really helps us with the integration. Every once in a while we'll find that that is the case with a rectangular box. However, you're going to see that's really not necessary as much. But as we have this x, y, z squared, as we integrate with respect to x, we'll get an x squared all over 2. And we're going to be plugging in a 1 and a 0 here. And plugging in that 1, of course, right in here. You'll get 1 squared all over 2. That's just a 1/2. Plugging in a 0 would wipe all that out. So this is a nice, quick little fundamental theorem that I hope you can do in your head. You don't have to write that out. But then what? Well, we'll say, next we're going to integrate with respect to y. Well, as we do that, you can see that we're going to bump this up to y squared. Divide by a 2, we'd have 1/4 y squared z squared, and we'll be evaluating that between -1 and 2. And as we do that, of course, when we plug in a 2, we could have our 1/4 and our z squared out here, but we'd have a 2 squared minus a -1 squared, and that's a 4, and that's a 1. 4 minus 1 is 3. It doesn't take you too much to see that you'd get a 3/4 z squared. And then what? Well, we just have to finish this up. We can, bump this up to z to the 3rd, divide by a 3. We'd have a 1/4 z to the 3rd. And as we plug in our 3, of course, we'd have a 3 cubed, which is 27. We'll have a final answer of 27 all over 4. And, that's all well and good. You'll have some problems like that. But in all honesty, you're not always going to have, a rectangular box that your region is going to be integrated over. Take a look right here. Of course, a triple integral can be defined over a general bounded region E. This is a type 1 solid region where Z is bounded between 2 curves, a type 1 solid region. And what you're going to see very quickly is that your Z will have an upper and a lower bound, but those upper and lower bounds aren't numbers necessarily, like we had earlier. Maybe they are functions, and they're curves, in other words, and that's what you're going to see for your boundaries. Now, outside of that, and this is the critical part, in a type 1 solid region, if you have Z bounded between two curves, you can project this solid region onto the XY axis. It's as if a shadow is coming down. You can see in yellow we have region D. And, you know, there are two ways you can look at this. A lot of books and calculus professors will say it's almost like a light is shining onto that, you know, solid, and D would be the shadow. Other people will describe it as if there's like a great garbage wall compactor coming down, smashing this solid onto the floor here of the XY plane. Regardless of how you look at it, you get the same thing. You'll have this area region of D, and that's where then it's going to revert to what we were doing earlier with our double integrals. And then you can have a type 1 or a type 2 region. We will see that, in fact, right now as we pick up with our next example. And we're going to look at that in some detail. So it says, evaluate this triple integral over a solid E. And E is the solid bounded by a cylinder, y equals x squared. Well, I hope you remember you know what y equals x squared would look like. Y equals x squared, of course, you know, you could have this, and maybe I'll change colors to really make it stand out. Y equals x squared would look like so, but you know what? You'd have all of these parabolas. So you have this parabolic cylinder, and so, you know, that's part of the solid, but then you have this plane. Y plus Z equals 4. And that means Z would equal 4 minus Y. And you can think, well, what does that look like? Well, you know, that, of course, is a flat surface. It's a plane. But very nicely, as we're starting these problems right here, they've actually graphed it for us. And, you know, that Y plus Z equals 4, they've really helped us right here. You could see that you would get, by the way, if you just had y plus z equals 4, you could look at this as if you just had the z and the y-axis. You could see that if you plugged in y equals 0 or z equals 0, you would get intercepts of 4, and, you know, it would look like a line here. But this is a plane, so you'd get really this whole big plane cutting in right here at y equals 4. Right up here is z equals 4. So that plane is going to cut into that parabolic cylinder, and this is the shape that you get. That parabolic cylinder is sliced by that plane, and you get something that looks like what they're depicting right here. And they're saying, hey, could you, and by the way, z equals 0 is really the XY plane down below. It's the XY axis that we've graphed over so very often. So, you know, as we're graphing over this, hopefully you can see this solid, and, you know, you can see it is a type 1 solid. And it's a type 1 solid because, I'm going to change colors right here, really make this jump out, I hope. Let's just say that Z's up here on that plane, Z's down here on the floor. So you can see more or less that your Z's are bounded in that regard. And, you know, that's hopefully really going to help us out quite a bit. So let's try to work this thing out. We could say, well, we're going to have a domain D that we're going to be integrating over, and we're going to talk about that in just a moment. Your z boundaries, well, we're going to go from z equals 0 where is the top of this solid? Well, it's the plane. It's the plane right here. It's going to be z equals 4 minus y. So we're going to be integrating in that regard. And, as we're trying to take this a step further, as we're looking at the domain D, the domain D is in green. In green, you can see that, if we shined a light on this, and maybe that's harder to imagine because the solid's actually on the floor where this shadow idea might not perhaps fit quite as well. But if we were to, have light shining straight down, in green would be where that light would be blocked out, of course. But the same idea of having a wall come down and smash this solid, it would go in green. So this domain D, as we're looking at it, it's going to be this parabola that's coming from the parabolic cylinder. But notice it's going to have your y equals 4 at the top right here. So we'd have our y equals x squared, and we've got y equals 4. So that's really going to come into play. That's hopefully something that we can see right there. And that's our domain D that we're integrating over. Well, as we go ahead and we work this out, look, antiderivative, this would be z squared all over 2, and we're going to plug in 4 minus y and plug in this 0 right in here. And, it doesn't take you too long, plugging in a 0. I think it's pretty evident that you're just going to have your 4 minus y squared all over 2. And then we're going to have to continue on with this. Well, the big question is, now we're back to an older problem. We're back to really what we were doing with our double integrals. And hopefully as you're looking at this double integral, as we have y equals x squared equals 4, hopefully you can see that we could make vertical lines, make this a type 1 boundary that we saw with the double integrals. In other words, your y's are always bounded between up on top y equals 4 and down below you'd have x squared. So, we could definitely come into play with that. Then what? Well, you could say all such vertical lines are going to go from here to here. And that's going to be, as you'd solve, 4 equals x squared. Well, you could see x could be plus or minus a 2. So we're going to go from negative 2 to positive 2. And, right now, working this out, I hope, would be, somewhat routine as we'd finish this. Hopefully we could finish this rather quickly. For the sake of time, I'm just going to say we could use our TI-89 to finish and get 2048 all over 105. What would we have to do otherwise? Well, you'd have to expand this and say it's 16 minus 8y plus y squared. Divide all that by 2 and work it all out. Could you work it out by hand? Of course you could. But for the sake of time in this video, we're going to let the 89 finish it off. Real quickly, just setting up this last portion of the video, you could also have a type 2 boundary where your your x's going left to right are bounded between two curves. And then what? The shadow would be projected onto a zy axis. So wherever you have boundaries, like if you have an x boundary between two curves, you're going to project that into the plane without that variable. So if x is between two curves, you're always going to have a region on the zy axis. We're going to pick up and actually look at this same problem that we just had, but rework it as a type 2 region. And we're going to do that in just a moment.